Let's start. Welcome everyone to today's GOCC. It's my pleasure to have Josef Küstner here from University of Vienna. He will talk about lattice paths and negatively indexed weight-dependent binomial coefficients. But before I hand over to Josef, let me remind all of you of our community statement. We have 3 guiding principles. Those are: we are all learning, everyone has something to contribute, and no one has all the answers. About questions, you can either interrupt Josef directly or ask in the chat. We will monitor the chat and then we'll hand the question to Josef. With that said, Josef, please take it away.
Thank you very much, Stefan, for the introduction, and thank you all for letting me speak here. I think that's very nice, a very nice graduate seminar and very nice guidelines. So I'm talking about lattice path and negatively indexed weight-dependent binomial coefficients, which is a very long title, but let me start only with binomial coefficients at first. Okay, so very briefly, the binomial coefficients for nk bigger or equal to 0, defined like this, I think you all know them, and they count lattice paths in the integer lattice, and starting at 0, 0, ending at k n minus k. So the number of paths from 0, 0 to k n minus k with steps going right and steps going up are n choose k. Now the question that one could ask is, how can we generalize this model for n and k integers? So n and k are not restricted to be non-negative anymore. What is happening then? Okay, a little outline how my presentation is built up today. I will start with the binomial coefficients, how we generalize them for nk integers. Then I will proceed to q-binomial coefficients. And then I will proceed to what we have done on this topic, weight-dependent binomial coefficients. They again have some special cases like elliptic binomial coefficients and symmetric functions. And this is joint work with Miso Yu and my PhD supervisor, Michael Schlosser. Okay, let's start with binomial coefficients. So in 1992, Daniel Loeb, he asked himself the question, so what can we say about the binomial coefficients if nk are not restricted to be non-negative? And he defined them in a way such that it works very nicely. So he said n choose 0 and n choose n is equal to 1. And for all the others, we can say we have the usual 3-term recurrence for the binomial coefficient. So n plus 1 choose k is equal to n choose k plus n. Okay, but how can we get from this to the negative values? So how can we compute them? I will do some very easy examples. So for example, here's nothing negative appearing, but what is 0 choose 1? So we know that 1 choose 1 is 1. We know that 0 choose 0 is 0 from the initial conditions. And so we can compute 0 choose 1, which is now only 0. Okay, now we can do some negative numbers. We know that 0 choose 1 is 0 from example 1. We know that minus 1 choose 0 is 1 from the initial conditions. So we can compute minus 1 choose 1, and it will be minus 1. Okay, another example. Now we take the recurrence for 1 choose 0 equal to 0 choose 0 plus 0 choose minus 1. So we know that 1 choose 0 is 1 from the initial conditions, the same for 0 choose 0. So we can compute 0 choose minus 1, which is 0. Okay, example 4. 0 choose minus 1 equal to minus 1 choose minus 1 plus minus 1 choose minus 2. So now we want to compute minus 1 choose minus 2. We know from example 3 and from the initial conditions that the first two are 0 and 1. So we can compute minus 1 choose minus 2, which is minus 1. Okay, and we can go on like this forever and compute all the examples, but I let Mathematica do that, for example, and we get this number array for the binomial coefficients for n plus k and k. So, and what we see here, if you look closely, that there are principally 3 regions. Like the red region is the very usual region that we know already. It's Pascal's triangle flipped around. So you can see that's here 1, then 1, 1, 1, 2, 1, 1, 3, 3, 1. It's just Pascal triangle. Then we have the green region, where we have again Pascal's triangle, but now with some signs like 1, 1 minus 1, 1 minus 2, 1, and so on. And we have the blue region, where we again have Pascal's triangle flipped around a little bit. So like 1, 1 minus 1, 1 minus 2, 1, and so on. And we have a lot of regions where there are only zeros. Okay, since we know that all of them correspond to Pascal's triangle, we can express all of the regions with binomial coefficients with positive entries or non-negative entries, and this is working like this. The red region is the usual binomial coefficients that we know. The green region, here we can compute n to k with the sign -1 to the power of k, and then some binomial coefficients where both negative. And the same is happening for the blue one. Here we have -1 to the power of n minus k. Okay, and there's a theorem by Sprugnoly that expresses exactly these correlations that I just showed you, these reflection formulas. So n choose k is equal to n choose n minus k. That I didn't show that, but that's clear. And then we have the other two, but there we have a lot of restrictions. So k is bigger equal to 0 and n minus k is bigger equal to 0. And we can fix then that by introducing a sign. So what if k is smaller than 0? Then we have a problem because we get -3 choose -5 is equal to -3 choose -5 if we take one of these formulas. So we fix that by introducing a sign. So the sign of n we define to be equal to 1 for n bigger equal to 0 or -1 if n is smaller than 0. Then we have the theorem by Sprugnoly in full. So for nk integers, we have these 3 reflection formulas that are always true now. And Loeb, who introduced this kind of binomial coefficients, he also gave an explicit formula in terms of gamma functions, but I just wanted to show it to you. It's not so important for us now. So one has to take the limit because otherwise one would have negative values for the gamma functions, and that's not good, I would say. The second one here, where k is smaller or equal to n. So it goes from n to -infinity. So we have the interpretation of the binomial coefficient with values, with integer values as the coefficient of x choose k, x to the power of k, y to the power of n minus k in the expansion 1 if k is bigger or equal to 0, or 2 if k is smaller than 0. And now we want to introduce a lattice path model. So n choose k, now we take the absolute value because we are counting something, and it counts lattice paths from 0, 0 to k n minus k, and using the following steps. So if n and k are both positive integers, we take steps that go up and that go right. So like, for example, a lattice path can start from here and go here, up, here, here, up, here, like this. The very usual thing to do. Now, what if n and k might be negative values? Then we cannot take the usual model that we have. So for some, if you go to the right down region, to the east-south region, then we take these steps. So we take down steps and we take like east-south steps. For example, a path can look like this. It starts here and goes down, then east-south, down, east-south. Okay, that's a valid path in this model. What's not a valid path would be like if you go first to the east and then south, east, south, something like that. This is not allowed because we always have to follow the arrows here in this picture. But there's a third region where we can take west steps and northwest steps. So for example, we start here, go west, again west, northwest, west, northwest, for example. This is a valid path. But what we cannot do is go up and then west. This is not allowed because we always have to follow these arrows. And now this is the full description already. So n choose k, and the absolute value of it count lattice path from 0, 0 to kn minus k for all integers k and n. So it's not restricted to be positive anymore. So one example, the binomial coefficient of -2 choose -4 is equal to 3 plus 3. And there are indeed 3 paths from 0, 0 to kn minus k, which is in this case -4, 2. Yeah, so it's always following the lines that I drew before.
What if k and n minus k are both negative? Because then I don't have a path, so there was nothing in the
exactly.
Four.
Then there is no path. I think we can see it like here.
Ah, this is the 0, 0 area. Yeah.
This is the 0, 0 region here.
Right here, yeah.
K and n minus k are negative, then we don't have a. So we can compare this here. Now you see why I took n plus k choose k and not just n choose k, because here we can see the correspondence. And we can also see already the signs where they are. And we can also deal with the signs. So we define the sign of a path now as the number of diagonal steps that we take. So in the positive region, again, here, there will never be a diagonal step. So the sign will always be positive. Okay, and then we get the weighted counting. So we sum over all paths from k to n minus k and take as a weight -1 to the, like the sign of the path. And then we get the binomial coefficient and we don't have to take the absolute value anymore. And the binomial expansion that I showed you before also have a combinatorial interpretation as generating functions for fixed n over all k. So I will do just one example. If I think n is equal to -2, we take this line here, and then we sum over all paths that go up to this line. But we have to restrict the line to one region, either here or in this direction. Okay, if we sum over all paths that go to the red line, then we will get this expansion here for n equals to 2. And if -2, and if we sum over all paths that go to the blue line, we will come up with this binomial expansion as generating function. So if we give them the weight minus the sign of the path and x to the k, y to the n minus k, which is the weight then. Okay, that's it for the ordinary binomial coefficients. Are there any questions so far? Okay, if not, then I will proceed to the q-binomial coefficients, which are an extension of the binomial coefficients. And this work also has been done before, so I will show you something that somebody else did before me. So for nk bigger or equal to 0, the q-binomial coefficients are defined like this. We take the q number of n and the q number of k, and yeah, and take the factorial. If you have not seen this, it's not important. So it's not important for this talk now. It's just some polynomials in Q, and they count Q-weighted lattice paths in the planar integer lattice, starting at the origin and ending at k n minus k. But now we take some weight to the path. So we are looking at all the boxes that are between the path and the x-axis, which is here. Okay. Here we see between the path and the x-axis, there are 1, 2, 3, 4, 5 boxes. Every box gets weight q, and we multiply over all the weights. So this path has weight q to the power of 5. And if we sum over all paths from 0, 0 to k, and then we will get the q-binomial coefficients. And again, we can ask the question how we can generalize this model to nk integers, of course. And very recently, 2019, Sam Formicella and Armin Straub, they defined these q-binomial coefficients that work now for integers n and k. So q now has to be invertible, and they can be characterized recursively again by this recursive definition that we had already for the binomial coefficients. So n choose 0 and n choose n will again be always 1. And then we have the recurrence relation, same as before, for all other values. Only now we have here the weight q to the power n plus 1 minus k. That's how we get the q-binomial coefficients. So this is, if you have never seen the definition from before, this is enough for the definition. Okay, and we will do the same examples as before, only now we have the q weights. Okay, so at first we compute 0 choose 1, because we already have 1 choose 1 and 0 choose 0 from the initial conditions, and we get again that 0 choose 1 is 0. Now we take negative values. So -1 choose 1 we now want to compute, because 0 choose 1 we have from example 1 is 0, and -1 choose 0 is 1 from the initial conditions. And now we have this power of q, which is q to the power of -1. So we can compute -1 choose 1, which is now minus q to the power of -1. Okay, next example. We take the recursion from 1 to 0, and we now want to compute 0 choose -1. So 1 choose 0 is 1, 0 choose 0 is 1 from the initial conditions. So we can compute 0 choose -1, which is 0. And example 4, same as before. So we now know that 0 choose -1 is 0 from example 3. -1 choose -1 is 1 from the initial conditions. And then we can compute -1 choose -2 now in the q case, which is equal to minus q to the power of -1. Okay, and again, we can go on like this forever, or now I give you a table. The table is now much smaller than before because it gets bigger. The values get bigger, and we see again the 3 regions: the red region, the green region, and the blue region. Now in the red region, we have polynomials in q, and in the green and blue region, we have polynomials in q just multiplied with some power of q to the power of some minus thing. And again, we have some not so easy to see anymore, but still some easy reflection formulas. So if we look first at the red region, this is the usual region we can describe as the q-binomial coefficient n choose k. Then the green region, we could compute them with positive values. So like if we take, instead of n choose k, we take -1 to the k q to some power, and k minus n minus 1 choose k. K minus n minus 1 will then always be positive, k as well in the green region. So we can compute them also like this. And for the blue region, there we also have such a nice reflection formula. And if we introduce signs again, then we get this theorem by Formicella and Straub. So n choose k is equal to n choose n minus kq. And the other 2 reflection formulas, they still hold. Only now we have this power of q here, also here this power of q. The rest is just the same as in the ordinary binomial coefficient case. And the sign is again 1 if n is bigger or equal to 0, and -1 if n is smaller than 0. So it's never, the sign is never 0, just want to mention. Okay, and they also found an explicit expression for the q-binomial coefficients. But first we have to extend the definition of products. So if a product goes from L to m minus 1, we distinguish now if m is equal to L, m is bigger to L, or m is smaller to L. I don't know if you have seen this before, maybe yes. So if m is bigger to L, in this product, then we take the usual product, AL times AL plus 1 and so on until we entered AM minus 1. If M is equal to L, we just take the product to be equal to 1. And if M is smaller than L, then we go backwards the product and we take it to the power of minus 1. So we start with AL minus 1, AL minus 2 to the power of minus 1, and so on until we entered AM to the power of minus 1. And the q-Bochhammer symbol we can define as product of from 0 to n minus 1 of 1 minus aq to the power of j, so the aq-Bochhammer symbol, which is by the definition of the product defined like this here. That maybe you have seen before. And then we can look at the q-binomial coefficients. So if n and k are bigger or equal to 0, then they are just defined with Bochhammer symbols. But there's a problem if n is smaller to 0, for example. So I've written it down here. Because q(n), so the q-Bochhammer symbol of q(n) goes to infinity. So we have a little problem here, but we can fix this again with a limit. So we take the q-Bochhammer of aq, n, aqk, and aqn minus k, and take the limit of a to q, and then it works fine for all integers n and k. So they also found an extension of the binomial theorem that Loeb showed for the ordinary binomial coefficients. Now it's a little bit trickier, but it's also a well-known fact. So we take x and y to be non-commuting variables. So if we interchange y and x, then there is a q entering here at the left side. Okay, x and y now have to be invertible. And then we can say for all n integers that x plus y to the power of n is equal to this sum from k bigger or equal to 0 over binomial coefficients, and choose k, and x to the power of k, y to the power n minus k, or we can go like in the other direction. So we start at n and go down. So we start at n, go to n minus 1, n minus 2, and so on until infinity, and we also have the same expansion. Also have an expansion. So we can say that n choose k, q is the coefficient of x to the power k, y to the power n minus k in either 3, in the expansion 3, if k is bigger or equal to 0, or in 4 if k is smaller to 0. Let's come back to the lattice bars model that I introduced before, and we take some q weights here. So like in the ordinary case, if we go only to the east and to the north, then we'd give a q weight to each box. So what I mean by that is again, so if we have a lattice bar starting at 0, 0, and then we go, for example, east, north, east, east, north, east, then we look at all the boxes that are below the path, and between the x-axis, this one, this one, this one, this one, we multiply and get as the weight of this path q to the power of 4, like as we have done before. Okay, what if the path goes down? So for example, we could give q weights here, but what do we do there? So there we have a problem because the arrow is going directly through the box. Okay, then we take a little trick. So we don't take diagonal steps anymore, but we make them go first to the east and then to the south. So here we had diagonal steps. Here they go to the east and to the south. Just be aware that now in this region here, every east step has to be followed by a south step. Otherwise, this would not be the same model anymore. So if we go here, we have to go south. If we go here, we also have to go south afterwards. This we have to keep in mind now. The same is true for the other region. Again, here, I mean, we don't take diagonal steps. We take now north and west step combination. And we also have to be aware that if we once go north, then we also have to go west. Okay, every time we go north, we go west also afterwards. And now we can give q weights to the boxes. This was maybe too small. I can zoom in maybe a bit. No, I cannot. So here we give q to the minus 1 as weights. And I do an example. For example, we start the path here, go south, south, east, south, east, south. So we cannot only go east. Then we take all the boxes that are between the path and the x-axis. So this one, this one, this one, this one, this one. We multiply, and the weight of the path will be q to the power of -5. Okay. And the same is happening for the other region there. We also give q to the power of -1 to the boxes. I only took the boxes here because there never a path will go on top of that. So an example I can do, we start here, we go west, we go west, we go north, we go north. No, we don't, because we are not allowed to, we have to go west. We can go again northwest and stop here. Then we look at all the boxes that are below the path and between the x-axis, here, here, here. And the weight of this path will be q to the power of -3.
I have a quick question. So in my my southeast quadrant, all of my paths need to have weight because like I'm forced to go down, except for like the trivial, unless I'm like on the y-axis, all of my paths need weight. But if I'm in the northwest quadrant, I'll have some paths which have no weight.
In the northwest, no, yeah, there will some paths that have no weight, but only trivial ones, only the ones that go always to the west.
Right, because I can't go north without also going west.
Exactly. If you once go north, then you also go west, and then you have a weight. Yeah.
Okay.
Very good question. Thank you. Yeah, and if we sum over the weight of all paths from 0, 0 to some k and -k, can be any integer, we get and choose k again the absolute value, because we didn't introduce signs so far. And we do the example from before. We had these 3 paths from 0, 0 to -4, 2. Now we don't take diagonals anymore. We take them up and north and then west. And we give the q weights to this path. And if you look at the weights, for example, this one here will have its weight q to the power of -5. And this is exactly what we get in the q-binomial coefficient case as well. So we sum over all these weights. This one will be here, this one will be here, and this one will be here. Okay, and in general, we have n choose k, q is equal to the sum over all paths from 0, 0 to k and -k. And then we take again this -1 to the p, which was diagonal steps, but we still remember what were the diagonal steps, and the weight of the path. Okay, so now finally we are ready for the weight-dependent binomial coefficients that I have promised, which is our part here at this work. We don't take diagonal steps anymore, so we also have to change the outline a bit. It's better. And now we do the weight-dependent case. So it's very weight-dependent. So we again will give weights to the boxes, but now every box has its own weight. So like this, we call them W of ij. So for example, this box here is box 1, 1, it gets weight W1, 1. Okay. And what do I mean? I mean, again, so we start at 0, 0, we take some path. For example, we stop it here. We look at all boxes that are between the path and the x-axis. And the weight of this path here will be W21 times W31 times W32. Yeah. And we want the weight-dependent binomial coefficient that looks like this. Now we have replaced the q by a w with the weighted counting of paths from 0, 0 to k and -k. Okay, how do we do that? So if k is equal to 0, that means that we are on this line. Then the weight will always be 1, and there's only one path to k and -k, so it must be 1. If we have n choose n. That means that we only have east steps in the positive case. Then there's also only one path from 0, 0 to kn minus k with weight 1. So the binomial coefficient, the weighted binomial coefficient also has to be 1. And for all the other cases, we have again this recursion formula. Now we have here like more complicated weight. Where does it come from? So if we take all the paths that start from 0, 0 to and go to kn minus k, so they end here. So we have to distinguish either the last step comes from south, like this one here. So the path before like ended here. Then we take this one here in the recursion, n minus 1 choose k, test k east steps, and it goes to n minus 1 minus k. Or the last step can come from the rest. So the last step is an east step. Then we take all the paths that go from 0, 0 to k minus 1 n minus k. They are counted by this one here, by this guy. And we also have to take into account these weights that are below. And this is just what this product is telling us. Okay, and we can now define it also for all integers. So as I said before, n choose 0 is equal to n choose n is 1 for all integers. And for all the others, we can do this recursion formula. Now I have introduced this big W. What is this? This big W is just a product over small weights, WSJ, which are like, it's like one column that I do. And we call the big W's big weights and the small W's small weights. And yeah, so for the nk bigger or equal to 0 case, this was already done by my PhD supervisor, Michael Schlosser. And he had this theorem that the weight-dependent binomial coefficient, it counts lattice paths from 0, 0 to kn minus k, given these weights that I just showed you before. This is one example here. So the weight of this path is W21, W31, W32, W41, W42, or expressed as these big weights. And the weighted counting, so we sum over all paths and take the weight is n choose k. And now we again ask this question, as always, how can we generalize this model to nk integers now? So one key observation is that for the big weights, we can do this trick or this extension for the definition of product. So if t is greater to 0, then we take this small weights, like here, like here, very usual. So this column goes this column. But if t is smaller to 0, then we have to have some minus ones, but it's not so important now. Okay, we do the examples from before. So the very easy example where we know already 1 choose 1 is 1 from the initial conditions. We know 0 choose 0 is 1, and the big weight 1, 0 is 1 that comes from here, because t is equal to 0 here. Okay, so we can compute 0 choose 1, which is again 0, as also in the ordinary and in the Q case. Then we want to do some minus signs. We know that 0 choose 1 is 0 from example 1. We know that minus 1 to 0 is 1 from the initial conditions. So we can compute minus 1 choose 1, which is now minus this big weight at 1 minus 1, or expressed as small weights, we can say minus small weight of 1, 0 to the power of minus 1, because the product goes down. Example 3 now gets, so 1 choose 0 is 1, 0 choose 0 is 1, and we can compute 0 choose minus 1, which is 0 now. And example 4, we know that 0 choose minus 1 is 0. We know that minus 1 choose minus 1 is 1 from the initial conditions. And then we can compute minus 1 choose minus 2, which is equal to minus the small weight. at -1 to the power of -1, because we have to bring it to the other side. And again, I computed this table. And again, we have these 3 regions, but it's not so easy anymore to get reflection formulas here, because they really look different now. Also, what's not possible is, so we had always this n choose k is equal to n choose n minus k. Also not so easy anymore. Where's one example? One example is like this here and this here should be equal, but it's really not equal. Yeah. So we have to find some tricks for that. The first reflection formula. So we take this reflection rate of ST, which is equal to just the ordinary rate that we had. We interchange S and T and take it to the power of -1. And then we have the reflection formula. We have n choose k is equal to n choose n minus k, but in the right side, we exchange the W by this reflected rate. And we multiply the whole thing by some big weights. This is working now. And yeah, I think I don't have time to explain it, but this is like we can prove this very combinatorially with the lattice path model, which is, I think, very nice, but I will skip that for today. Here you can just have a look how this might work. And the other 2 cases that I did in the ordinary and the q-binomial case, they also work. We again have to introduce some rather complicated reflected weights, and then we have the same reflection formulas again. Here we have the reflected weights, and we have to multiply the whole things with some big weights. So it's still working. It's a generalization, but it's a little bit more complicated, a little bit more to do. Then the binomial theorem, we also were able to generalize in the weighted setting. It gets much more complicated. So x and y are again non-commuting variables. So if we interchange y and x, then we here get a w11. So in the q case, we only had a q there. Now it's a w11. And if we interchange the x and the weight, then this s has to be is like plus. You have to take +1, s +1. And if you interchange it with the y, then the t is +1. And then if we have these 3 conditions, we get for all n integers this like very nice looking binomial theorem, which looks just like the other cases, the ordinary binomial case and the q-binomial case. We just now have this weight-dependent binomial coefficients and relations. So yeah. So we go again to the lattice. Yeah.
So in this case, our weights are. So what are weights mapping to? What's their image? They could be anything, right? So the W function maps into.
Yeah, so it could be anything. So for example, you can take all the weights equal to q, and then you will get back the q binomial coefficient. Or you can take all the weights equal to 1, then you get the ordinary binomial coefficient. Or you can take, just let it can be anything. So it are indeterminates. Yeah.
I guess I kind of want to follow up on that question, actually, because looking at that slide where my weights don't commute with my variables, it feels like it's kind of begging for them to be some commutators in some groups or something, where I don't necessarily commute with my commutator as well. And so have you taken a group and like thrown the commutators into these expressions?
No, not really. So we are dealing. So this so to be precise, these formulas here, these expansions. Yeah, there are in some non-commutative associative algebra. So to say.
Yeah, I guess it would be some kind of I think you need some non-commutative associative algebra.
Exactly. I think that might be the same like your idea. Yeah. Okay, thank you for the question. So now we go back again to the combinatorial model, and I guess you all know already what will happen. So we give weights to the boxes. So this case we have done before. Here we give this, just every box gets a special weight. So this one here, this one here is box 1, 1, so it gets weight at 1, 1. Or for example, this one here is box 3, 3, and it gets weight 3, 3. And for the others, now this is very small. Okay, we again take, so how do we find these values at first? Let's, for example, deal with this box here. This box gets weight 2, -1. Where does it come from? So we take the east-north corner of the box, which is at position 2, -1. And that's where it comes from. And here in this region, we have always to take the power to the -1. And what we do, so for example, if we have a lattice path, let's go south, south, east, south, east, south. Then we look at the boxes that are between the path and the x-axis, like this, 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 this again. And the weight of the path is like the, again, just the product of all these weights. So 0, 1, 0 to the -1 times w, 1, -1, and so on. So we take all the weights that are between the x-axis and the path. And the same applies to the region here. We also take to the power of -1 here. So we have to do it because then it works out, and otherwise it doesn't. Okay, and then we can say the weight of the path is defined as the product that runs over all cells ij between the path and the x-axis, just like I showed you. We take the product of all wij's. These are the weights that are between the path and the x-axis, and we take them to some power, and we can express this with sine to the i-1 times psi to the j-1, which just means that in the positive, positive region, the northeast region, it will also always be 1. Here it will always be -1, and here it also will always be -1. These powers, I mean. And then if we give again this signs to the path that we have introduced before, then we get the weight-dependent binomial coefficient as generating function over all path, given this weight and given this sign. And I do one example, -2 choose -4 that we had before. So if we write this binomial coefficient out, then we get this expression here. And indeed, this works out with this path. So these are the weights of this path. We multiply over all weights, and then we can see where they are. Like the first one is this here at the bottom. This one here is, I think, here. And this one here is, yeah, I hope you believe me. It's just the same weights, and we get this for the weight-dependent binomial coefficients as well. And what we can do with this lattice path model is, for example, that we can have a convolution formula. So do I have time for that? Okay, let's maybe only look at this region here at first. So what we do is, at first, we take a path that goes from 0, 0 to n to jn minus j, which is here in the sum and here in the path. Then we have this m choose k minus j, which corresponds to this path here, this x and y's here in front and after. This just that the weights are shifted. Not so important for now. And also we have this product over weights, which just corresponds to the weights which will appear here between the path and the x-axis. Okay, and if we sum over all j from 0 to k, then we will end with all lattice paths from 0, 0 to k, n plus m minus k, so which are counted by n plus m choose k. And in the ordinary case, if you take all weights equal to 1, this is just the true fundamental convolution. And here in this picture, you see that this also works for the negative cases as well. But I will not go into detail. There's again another convolution formula. Now we sum from k minus m to n. It's so important now. So a little summary, what we know about the weight-dependent binomial coefficients is in the integer values. So we have this recursion formula. They're defined by the recursion formula. We have a lattice path model. Then we have the reflection formulas. We have the binomial theorem and the convolution formulas that I showed you at the end. And what's nice about this is that these results transfer to all specialization of the weights. Okay, so we get all these theorems to all specialization. And like a very easy specialization is if we take all weights equal to 1, because then we get again the ordinary binomial coefficients. If we take all weights equal to q, then we get the q-binomial coefficients. And then we can do more complicated things. But I see that I only have 2 minutes left, so I will very quickly go through it and just show you what we did. So we have mainly two important specializations, which are nice here. So we have elliptic binomial coefficients, which were the motivation for doing this whole weight-dependent thing. And also we can specialize to some symmetric functions. So elliptic functions, I will not do that. Okay, let me just go through the slides very briefly. It appears that elliptic functions, they naturally generalize q-analogues, which is true for hypergeometric series, which is true for some combinatorial models like non-intersecting lattice paths and plane partitions, but also for some special numbers as the binomial coefficients, for example, Stirling numbers, Lucas sequences, Lahn numbers. So there's a lot of research going on there. This field, and that's where the motivation came from to do that, because now we can just take the weight equal to some product, so fraction of products of theta functions, which you don't have to know, but just know that we can do that, and then we have the elliptic binomial coefficient, which comes out of that. And we have all the theorems that we had before now for the elliptic binomial coefficients. So we have reflection formulas, we have a binomial theorem, we have summation formulas. And the nice thing about this summation formula is that this true Vanderman convolution that I showed you before in the elliptic case is equal to, or is similar to a very important summation formula in elliptic hypergeometric series called the Frankel-Toraev sum. And the last thing that I also just briefly show now, because I'm running out of time, are symmetric functions. So if we take the weights equal to a s plus t divided by a s plus t minus 1, then we get for the nk positive case the elementary symmetric functions. But if we then take nk, then nk might be negative, something nice happens. So we don't have elementary symmetric functions anymore, but we get complete homogeneous symmetric functions. Also for the case n between n smaller 0 and k bigger or equal to 0. And the other region, which was k bigger or equal to n smaller than 0, there we also get complete homogeneous symmetric functions. And from the convolution formula, we can recover this very classical identity for elementary symmetric functions and complete homogeneous symmetric functions, which is just a consequence of the convolution for the weight-dependent binomial coefficient. And from the binomial theorem and using some operators, we can recover the generating functions for the e's and the h's. Okay, and the symmetric functions, their own have some very nice specializations, but if you're interested in them, I would recommend you McDonald's book. Yeah. So a little conclusion. So many results from Loeb, Formichel, and Straub in the Q and ordinary case, they can be generalized to the weighted analog, as I have showed you. The weighted analog in itself has some interesting special cases, as the elliptic binomial coefficient and the symmetric functions, the e's and the h's. The lattice path model can also be generalized. and it illustrates some properties of binomial coefficients with integer values. So we can use the lattice path model to interpret the binomial theorem, for example. And so like the people that came before us who worked with the binomial coefficients and the q-binomial coefficients, they worked with a different combinatorial interpretation. They took subset of hybrid sets, which is a generalization of ordinary sets, but they are just in simple projection to the lattice path models. So we introduced the lattice path model, and we also have this projection to the subsets of the hybrid sets. Okay, here's my references. And I thank you very much for listening. And if you have questions, then I would be happy to answer them if I can.
Let's
thank you very
thank the
much.
speaker. Thank you for this nice talk. Are there questions?
I have a quick one. Was the symmetric functions you obtain, is it the set of all symmetric functions or just the subset of them?
Only the subset, only the
Okay.
elementary symmetric functions and the
Okay.
homogeneous.
Thank you.
So that's all. Yeah.
Cool. Thank you.
Yeah, and maybe I can say this only works because the two of them have very easy recursion formulas. So like the binomial coefficients just with some weights, so to say.
I have one question. So you have shown us a two-dimensional path. So if we take more dimensions, I guess we get multinomial coefficients. And can you generalize the whole story there?
Yeah, it might be possible, but I haven't looked at this. So it was already quite complicated to deal with these weights in the two-dimensional case. So go multidimensional might be possible, yeah, I think so. But it's more complicated.
Thank you. Are there further questions from the audience? So if not, let's thank Joseph again. And we can stop the recording.